Hello, and thank you for attending this presentation on our work comparing modelled versus measured results on a real house. My name is BenAbel and I'm Technical Director at Hilson Moran. My background is in building physics and I've always had a real interest in trying to find ways to validate our predictive models. Now, this work was a collaborative project between Hilson Moran, Inkling Partnership and Loughborough University, and I'd like to thank everyone involved as this project relied on a collaborative approach to produce these exciting results. The start of the project goes back to the CIBSE Symposium in 2018, where Ben Roberts from Loughborough University presented his original work where he'd set up two test houses to replicate the loads and schedules of the TM59 methodology. At the time of this presentation, I remember it immediately got me thinking, if he's modelled some real houses to TM59, we could use this as a validation exercise to test how close our dynamic thermal models came up to reality. After Ben's presentation, I approached him with my idea, and I also contacted Susie at Inkling, as I knew she'd been instrumental in the TM59's production and would be keen to be involved. So from the initial idea, this is how we got our project started. So in this presentation I'm going to cover the following: how we set up the models, how the results compared to one another and what discrepancies we saw, examine any differences between the modelled and the measured data, and what conclusions we can draw between the modelled and the measured data. So this is an image of the two test houses and their floor plans. Although the houses were built around the 1930s, they were refurbished relatively recently with new windows fitted, a new roof and 300mm of loft insulation. The cavity walls were left uninsulated and the ground floor is a suspended wooden floor over a solid base. Previously there had been some air leakage tests on the building, and these came back with a result of around 15 metres cubed per hour at 50 pascals. So as you can see, it's a semi-detached house. The west house, the left in this image, operated as per the table. So we conducted three tests. The first test with the windows closed, everything else as per TM59. Second test with the windows opening for the natural ventilation, and the third test using the curtains to be drawn in a different schedule. So most of the results we're going to look at today are for the west house. The east house was basically used as a control with the windows always remaining closed, but again with all the TM59 schedules going on. For our tests we used two pieces of software, both TAS and IES, Dynamic Thermal Modelling softwares, these being the two dominant softwares for using TM59, both being CIBSE AM11 compliant and approved for Part L. And for this analysis, both Hilson Moran and Inkling supplied a user in each software. Now the analysis was carried out in two stages, a blind stage and an open stage. In the blind stage, all the modellers were given the same set of information, drawings, description of the constructions, where known, weather data, etc., and then left to carry out a TM59 analysis as they saw fit. At this stage they weren't given the actual measure results. Once all the blind stage results were completed, we had a workshop where we compared our initial modelling results with the actual measured results and revealing how close they were to the measured data. The next stage was an open test where, based on our blind test results, we then tried to bring the models closer to the real measured results. The weather data was supplied by Loughborough University. They have two weather stations on site. Both weather stations measured all the metrics we needed, so solar irradiation, dry bulb, humidity, wind speed, direction. The only thing it didn't have in there was cloud cover, so that was synthetically generated from the solar radiation data. There was also an additional temperature sensor in the back garden to account for any local temperature anomalies between the house and the weather stations on the university, which was about half a mile away. And from this we created a bespoke weather file to match the weather experienced by the houses. So looking at the initial set of results, so I'm going to look at initially these results from the living room, so you can see we have our 4 models results, 2 TAS, 2 IS, and the coloured ones are the model results, the dotted line is the measured. So you can see all the modelled results were fairly close together, but they were all some way out from the actual measured results, particularly, as we will see, on a hot sunny day we saw the temperatures being over predicted. So here in a bit more detail you can see the 4 model results were all in excess by several degrees of the measured results. However, over the course of the test the correlation still remained fairly good. When we looked at a cooler day, we get better matching, so some models were over predicting, some models were under predicting, but it was much closer around the measured results. So the initial good news was that all the models were predicting very similar things, irrespective of the modeler and indeed the modelling software. So that gave us confidence that, you know, neither modelers or modelling software were doing anything particularly strange, and the correlations remained fairly good, again irrespective of modeler or modelling software. So going on from this, we needed to understand what the discrepancies were and what we could do. So the first thing to look at was the environmental factors, so external air temperature, wind speed, radiation. So first set of results, so watch this point, we're now only looking at one of the sets of results, so this is from Modeler 3, rather than look at all 4, because they were all were exhibiting very similar trends. So in the living room, which is our south facing, we could see when we had a hot sunny day, so high solar radiation, high external temperatures, our model was overheating more than it should have done according to the measured results. So we had more than 70% of the time when the difference was more than 1 degree, when the air temperature was over 20 degrees, and also when the solar radiation was high, we tended to see these discrepancies between the measured and the modelled data. Looking onto the rear bedroom, so north facing, we saw a bit of a reverse. So despite it being a hot sunny day, the simulation was under predicting at points against the measured data. Now if we go on back to the living room and look at a cooler, cloudier day, and actually this day is actually relatively windy as well, we could see that actually we were under predicting at this point. So for the south facing room, the models were predicting cooler temperatures than the building was measuring. Similarly for the rear facing bedroom, when we got these cooler conditions, particularly in this case where we had a very, for May, quite a cold day preceding it, the temperatures for the modelling tend to diverge quite significantly from the measured data. So what do we draw from this is, in the south facing rooms we tended to overestimate the operative temperature. So the team pondered on what the reasons behind these discrepancies could be. Such things as thermal mass, solar radiation, the transfer of the G-value and transmission through the glass, and even potentially the curtains and blinds in their operation. So actually in the testing we looked at 8 different variables to test. Of these, 4 seem to bear the most impact on the results, and I'm going to look at these in detail now. So the first thing we looked at was the radiation data. when we compared our measured radiation data from the on-site weather stations against the CIBSE DSY file for Nottingham, which was the nearest DSY file, we noticed that the radiation, particularly direct radiation, was considerably higher than the CIBSE DSY, and whether this is some sort of averaging in the DSY or other reasons we did not know. So what we did in this case is we clipped the solar radiation never to exceed just over 600 watts a square metre, which is what we were seeing in the DSY, and we ran these results. So looking at the living room, so now the original model is the trace in red, the modified weather file is the trace in green. So for our peak sunny days around the 26th, 27th of May, our correlation improved significantly and didn't change too much on the cooler, less sunny days as expected. Conversely though, the rear facing north bedroom got considerably worse, moving away from the measured data. So it helped on the south side, it made it worse on the north side. So the next thing was to look at the glazing G value. So from the information we were provided, we think the glazing G value was about 0.72. To maybe allow for dirt on the windows, some of these patternings and stuff we see in the actual windows, we reduced the G value to 0.5 to see if it had an effect on the results. So looking at our south facing living room, again, when it's sunny, reducing the G value really helped the correlation, but when it was cloudy and cooler, it moved it away from the actual measured results. Similarly as before with the weather file, modifying the weather file, for the rear facing bedroom, reducing the G value moved the measured result, moved the model results away from the actual results. Next we looked at thermal mass. We'd done some initial tinkering around with the thermal mass, but it wasn't doing too much, so we went for a sort of extreme test. So we tripled the thickness of brick within the walls just to see what the effect was. So again, looking at our two rooms, in our living room, increasing the thermal mass on the sunny days, didn't really, made it fractionally worse in cases. It did tend to help us, as you expect, on the cooler days. It's retaining more heat, so it made a slight improvement on the cooler days. Not much change on the hotter days. For our north-facing bedroom, again, tended to help on the cooler days, and there's a small changes when it's very sunny. And finally, looking at the curtains, the effects of the curtains in the modelling, we weren't sure how if this was being done correctly in the models, because it's usually as part of the construction. As you can see here, there's gaps around the windows. The curtains never hang very tightly to the window, so there's a good chance for air movement. And so we increased the resistance because maybe we thought there was extra resistance in the curtains to see what happened. The answer was for the south-facing one, not a lot. Very close, minimal changes to the plots, both sunny and in the cooler conditions. And similarly for the rear bedroom, made it fractionally worse when it's sunny. In fact, fractionally worse right through the trace, but very similar results. So despite testing many variables, we didn't come up with the silver bullet which brought the results of our model data closer to the measured data. The results here are presented as just a small sample of the various combinations that were tested. The comforting thing is that from an industry perspective, is that all the models responded in a very similar way, irrespective of modeler or modelling software. However, broadly, all the models over-predicted temperatures when the room is exposed to hot sunny weather, and underestimated temperature when cooler overcast days, and overestimated the swing day to night. I guess the good news from an overheating perspective, this means that we might be over predicting the temperatures we might get in new developments in the day, and therefore we might be over specifying the facade performance or shading, etc. But conversely, we might be underestimating the nighttime overheating risk. For this particular building, there were many aspects that weren't completely known, such as the constructions, how the walls and cavities were actually ventilated, and these had to be estimated. The other thing to bear in mind is that this building is relatively old and doesn't represent the type of construction that we find today, particularly in high-rise curtain wall type developments. We're planning to do some further research into this to see if we can narrow the gaps in the way the models predict overheating. Something we're looking at is actually trying to get at the underlying governing equations to the software, as most of the programs used today were designed to predict building loads and primarily heating loads. Operative temperature, which has the added factors of radiant temperature, airspeed thrown in, might be proved to be ill-suited to the way these algorithms work and control the model. Despite the discrepancy we encountered, it was really pleasing to see how close all the models were in their predictions to one another, and hopefully this means we're giving our clients broadly the right advice. I'd like to close with a quote at the bottom of the slide, which I think encompasses what we're trying to achieve, is to be useful to our clients. And we can only do this if we're confident in the answers we produce, which I think this research has certainly given me some confidence that what we're doing currently is giving some good and reliable answers. Thank you very much.